Okay, this lesson is called New Ideas and Terminology, and it's a hodgepodge of little things, essentially from grade 9 to 12. Some of it might be like you look at it and go, I totally know that. Did I really show up to AP Calculus for you to teach that? And the answer is, well, I guess you did. You know what I mean? Like I'm just showing you little things that words we might not have used, ideas we might not have covered from grades 9 to 12. For instance, it starts off really easy. Oh, this is a great example. This is called increments, and you already know what increments are. I'm just giving it a new word that we really need. Like we're going to use the word increments in some big time tough situations, so we better get the word down pat right now. Increments are simply the horizontal change, the run, and the vertical change, rise, from one point to another. And if you're unimpressed by that, you should be. I could have easily said that in grade 9. Instead of calling it rise and run, I could have called it horizontal increment and vertical increment. Here it is formally. If a particle moves from the point, ooh, interesting. Yeah, they're sort of setting up physics and vectors here, the way they're rephrasing this here. If a particle moves from the point x1, y1 to the point x2, y2, the increments in the coordinates, delta x is x2 minus x1. There's that delta that maybe didn't come up quite often enough in grade 9 to 12, is delta means, well, that's exactly what delta means. Delta means how much did it change? It's a Greek letter, and whenever we use it to say how much did it change. And then delta y, y2 minus y1. So again, it's just the rise and the run. But we're getting ready for other stuff here when we call it increments. And here's an example in case that wasn't clear enough. Determine the increments from 9, negative 10 to 7, negative 4. So the delta x will be x2 minus x1, which will be 7 minus 9 is negative 2. Or maybe it's positive 2. If you went 9 minus 7, maybe you could get the increment as positive 2. See, it's not real clear on the increments which way to subtract. Huh? But I'm going to do the second point given minus the first point given just to stay consistent. And then delta y is negative 4 subtract negative 10, which when I punched in my calculator, I get 6. You're like, why didn't that y2 minus y1 thing come up before? Why did it not matter before which way I subtracted? You're always dividing by delta x. So if you got the sign wrong, you'd get the sign wrong on the second one too, and the two wrong signs would cancel out. So it wasn't really a problem when we did delta y over delta x, and it's usually not a problem here either. This thing either went negative 2, 6, or it went 2, negative 6, depending on which direction you want to talk about. So it's not really a big problem. You know, it seems like it's a situation, but it's not at all. Questions there?
So for consistency, we're going to do x and y2 minus x1 and y1.
Yeah, usually you just take the second one and subtract the first one. But you could totally reverse it. Let's say you look at the points and you're like, oh, it's easier if I do it the points the other way around. You reverse it and it's not a big problem because technically speaking here, the increments could have been 2 and negative 6. And you're just talking about, oh, I went from this point to that point instead of from that point to this point. So it's really not a big deal. It seems like, oh, the signs are going to be wrong. It's because the orders, you just did it in the reverse order, that's all. So it's not really a problem. Great question. Point slope equation of a line. Actually, I think some grade 10 teachers do teach the point slope equation of a line. I don't really know. I teach grade 9 and then grade 12, and all I teach is y equals mx plus b, you know, in both 9 and 12. And so in between, you might have seen this, which is point slope. So we often use equations of the form y equals mx plus b to describe lines. When we're doing lines, we often use y equals mx plus b. But there's another way, another form of the equation of a line, known as point slope form, can be useful. And if you've never seen it, when you do see it, you might be like, why didn't we use that the whole time? Isn't that actually a little bit easier to use than your y equals mx plus b? Well, it's a decision that is made in grade 9 to go, are we going to use this one or the other one? And overall, over all the grade 9 students, generally speaking, most people find y equals mx plus b easier to use. Now that you've seen the whole story from 9 to 12, you might immediately switch over and go, no, I like the new one way better, yeah? To arrive at point slope equation, we use the definition of slope. So instead of building the equation from y equals mx plus b, you could start with the slope equation, which is m equals y minus y1 over x minus x1. You're like, whoa. It's not x minus x1 and y minus y1. It's x2 minus x1 and y2 minus y1. I'm like, yeah, I know, but think of it this way. Let's say you got 1 point and you haven't yet figured out what the second point is. That's what this equation is used for. You're like, I know this point, but I don't know this point yet, or I want an equation for finding more points. And you could use this formula, but this is not convenient the way this is. So I'm going to move the x minus x1 over and make it y minus y1 equals mx minus x1. And once I move the y1 over, that might start to look familiar, because that's the transformation version of this. Up, down, right, left, vertical stretch. Now it's the same as all the transformations you saw in all the other stuff you did all the way along. And so that's why people like it, is because now it finally looks like the other equations you were doing all the way along. I just finished advanced functions, and when we talked about lines, usually we'd go, every other transformation we'd go, okay, right 2, up 7, vertical stretch 2. Every other function we did that with lines, I went, oh, just use y equals mx plus b, and acted like lines didn't fit into the transformation thing. Well, they don't if you use that equation. If you use this equation, it works exactly the same, and it's so nice. You just plug the point in and you're done. This equation is said to be in point-slope form. All you need is any point and the slope. If you're like, I'm really out of practice, I don't know how to use this, I'm going to show you in just a minute how to use it and how simple it is. And x1, y1 is any point on the line. Once they give you a point on the line, use it as x1 comma y1. Mx1 and y1 can represent the transformations on the line y equals x. Now lines are just another function we do transformations on if we use this version. Example. No, formal version. The equation y equals m bracket x minus x1 plus y. How many saw this in grade 10? Rings a bell. Yeah, there's one grade 10 teacher who I think uses this instead of the y equals mx plus b. That's fine. They're interchangeable, really. I'm going to do them both right here. So you go, now I see what you mean by they're interchangeable. You can use either one. Example. Determine the point slope equation of the line that has slope 4/3 and passes through the point negative 8, 5. Let's rewind to grade 9 for a minute. If I taught you in grade 9, what we would have done was go y equals mx plus b, and we would have gone y equals 4/3 x plus b. And then we would have stood there and gone, how do I get the b? And we would have been really stressed. And then I would have stood at the board and said something ridiculous like, oh, if we only knew an x and y, we could find the b. And there's the x and y. And we would have subbed it in, found the b. And it was one of the tougher questions in grade 9, actually. It was one of the brain busters from grade 9. So you could do it that way. The other way to do it is to use this new point slope equation where you go, okay, slope goes there, 4/3. This thing has been moved left 8. So what I need is a positive 8 in there. And it's been moved up 5. So I put the 5 right there. Transformation type thinking. Maybe you don't think that way. Maybe you'd go right to positive 8 here. I think most people, I got to go to negative 8. I use plus 8 there. That's fine. Done. Point slope equation of the line. See, much better than y equals mx plus b. Bang, done. You're like, well, what if I want y equals mx plus b? That's real easy. Distribute and collect. That's all. You just tidy this up and get rid of the brackets. So if you want, that's the better way to say it. Y equals mx plus b is just the version of this with no brackets. We just multiplied out the equation. Yeah? So not too complicated. There are other equations of the line available out there. We could rearrange this in other ways. One way we could say is, let's get all this stuff over to one side. Yeah? We could move it all to one side, because you see that sometimes. You definitely see it in grade 10 with the equations like 3x plus 2y equals 7. You know what I mean? Like they were set up in that format. So by rearranging the equation of the line, we could bring the x's and y's over here if you want. And that's called the general linear equation of the line. I did not memorize this in school, I must tell you. I didn't get too excited about general equation, because the one I knew was called, onto this next page, was called, I'll get to it in a minute, but here, general equation of the line. So if you want to do general equation of the line, you do the exact same stuff. You go, okay, put the m there, put the transformations in there, y equals 2/3 x minus 4 minus 5. If you love transformations, do it that way. If you don't love transformations yet, well, this is the first thing on your study list, your little study cards for the chapter, right? Is put this and go, exactly here. That's why it's in this special box. You want to make study cards? There's the first one in the box. Because it makes this question really easy, is you just sub the slope in there and you sub the point in there. Really quick and easy. Now, if you wanted to take this from this form over to what's called general equation, then you want the x's and y's over here for some reason. For some reason, we might want the x's and y's over there. And all you do to accomplish that is multiply out the brackets and collect things and move them over there. This particular PowerPoint doesn't handle it that way. It goes, oh, fractions, oh, fractions. One of the things we're going to get to the bottom of is fractions this year. And being able to handle fractions when they appear, instead of freaking out, I'm going to give you management techniques to go, how do we get rid of these fractions and be able to manage these things? Because I understood what the question was saying before the fraction showed up. I'm going to give you lots of management techniques. One of the management techniques in equations is you see a fraction like that, 2 divided by 3, just multiply everything by 3 right now. And if I multiply everything by 3, this becomes 3y, this becomes 15, and that becomes 2/3. Or sorry, just becomes 2 because the 3's cancel out. See how nice that is? Boom, fixed right up. So I use this opportunity in this PowerPoint to start showing off one of those tricks. Do you have to do that there? No, you could multiply out the brackets, you could bring everything over and multiply by 3 later if you wanted. But seeing through these questions, when you just divide by 3 in the question, I've eventually got to multiply by 3 anyways, so why not do it now? It only gets multiplied by the thing out front. You say, well, why doesn't the inside get multiplied by that? It's going to. I'm just not done yet, so it's still sitting out front. So then I multiply into the brackets and bring the x and y's all to one side to get what's called general equation. If you can get it where the x is not a fraction, the x coefficient, and it's positive, then it gets to be called standard form. This is why I didn't memorize general form, because I realized something in all this. I don't have to know general form as long as I know standard form. So from then on, whenever they didn't want y equals mx plus b, I'd just go right to standard. I'd go, all the x's and y's over here, x has got to be positive, and x has got to be not a fraction. Yeah? How do you get it like that? Well, if it happens to be negative, you just multiply through by negative. Happens to be a fraction, you just multiply through by the denominator. So you can always fix it up that way to get what's called standard form. If this is new, don't freak out about it because it's not particularly complicated. It's really just move everything over to one side. And we used to do it in grade 9. It was only about 10 years ago we stopped teaching this in grade 9 and we just sort of left it for now. Yes, question?
So is standard form the point slope equation?
Standard form is not the point slope. Point slope is still y equals, like y equals mx plus b, but the point, you can see the point sitting there as opposed to y equals mx plus b. Standard sort of comes later and you go, okay, you want standard for some reason. Then you're going to find out there's reasons why we might want standard. When you want standard, then get rid of the brackets, multiply it all out, and get all the x's and y's to one side with this x1 being positive. Again, for some reason. And because there's ways to look at this equation and really see through what's happening if that x is positive. Okay, so there's more to the story here. For now, we'll just say this is standard form of the equation. Other questions there? Regression analysis. Well, more of this in the next lesson, but I want to talk about real life for a second. So I'm going to switch out of the PowerPoint and just draw something to try and give you an idea about what we're trying to accomplish here. And I bring up biology as an example because biology is a perfect example of how things cannot work out the way we expect. You know, biological processes just cannot be trusted to follow the rules exactly, you know? And I think about, I'm going to use rabbit population as my example and not get addicted to coronavirus examples, although this applies to coronavirus as well. If you had an equation to describe what the rabbit population is going to do, it might be a perfect curve. Well, the rabbits aren't going to follow the curve. That's not going to happen. They don't care about our curve, and certainly the coyotes that are hunting the rabbits don't care about my little curve. So if we actually went out and measured how many rabbits were out there, which isn't that difficult to do actually, you can actually do a pretty interesting way to count these things. You know, you count how many are in one little section and just extrapolate out and say, oh, there must be this many. There's obviously measurement errors coming here. But when you go to graph it, you might find over time that the population of rabbits that we expect to be exponential does something like that. You know, good years and bad years, areas where there's more coyotes or less, there's food in this area, there wasn't food, something bad happened, and the population instead does something like this. And in our mind we go, oh, it worked. Our equation is there. It's laying right there. It's this regression curve where we go, oh, it really is something like that. And yes, there's errors along the way. And again, biology is the perfect example of when this happens, is that things aren't going to go perfectly, but we do a regression to say, here's what the basic curve looks like of the whole situation. Just to get sidetracked by coronavirus for a second, this is how the science table knows what's about to happen. When they say, folks, we got to shut down, it's because they look and go, nobody else can see what's happening here? Like, it's bad. And tomorrow's not going to be better. Next week's not going to be better. In fact, the sooner we get going, and we found out. We found out in March a couple times. We waited too long, and then to get it back, like, good luck once this thing's going that way to get it back. If we really wanted to keep that thing under control, we should have shut down about here, and then we could have maybe been back in school for June. You know, and that wasn't their strategy. I'm not criticizing the strategy. I'm just saying this is how the science table knows. They look at this and they stare at it for days and days on end, and they do every little math they can think of, and they go, oh, it's bad. Yeah? And it's not going to get better. It's about to get worse. We're maybe in that situation right now. You know, things were going well, and now it's starting to do this, and winter's coming. Yeah, and here we go. All right, that whole long speech to basically describe one single word. It's a tough word to define. Took me 3 or 4 minutes there. I went from the beginning again, so let me just scroll through to the point that we were talking about there. Not this point. The point, where were we? Regression analysis. Regression analysis is the process of finding a curve to describe the trend in data. It's the process of taking the math you've learned in high school and applying it to real world situations and go, here's how we can take this math and do actual things with it. See, high school math is frustrating. We give you a function, then we give you another function, we give you another function. Like, when does this end? And the answer is when we give you enough functions that you can actually do something. Now we've done that. We've given you all the functions, all the advanced functions. We've given you everything you need. That's not true. It's not everything. We've given you most of what you need to now step out and go, okay, let's go. Let's do some stuff now, okay? In regression analysis, the curve that is fit to the data is called the regression curve. Easy to remember. And they put a nice picture like mine on there where they go, doesn't it look like a straight line? I know there's errors here, but it looks like a straight line. And so he's drawing the regression curve up there. The regression curve can be linear, quadratic, exponential, logarithmic, sinusoidal, any type of curve that you've seen so far. And if you're like, oh, that's why in all through the grades we've been learning all these different things, because there's different situations. Some situations, like a ball flying through the air, follows a quadratic. Some situations, like coronavirus, follow an exponential. Some decibels, things like that, follow logarithmic graphs. Sinusoidal, well, anything that has circles and triangles is doing this. Any waves is going up and down like this. And we'll get back to trig in a couple days. You know, we'll make sure you got your trig up to date. So when analyzing real world data, it's usually difficult to find the regression curves equation without the use of a computer. I've done one of these once in all of university. They made us find the regression curve and go through and actually analyze the points. Ours was 20 points, only 20 points of data, and it took forever to do it by hand. I know why they made us do it. One time, let's see that you know how to find this curve and find the best possible curve for it. Using calculus and some crazy algebra, we were able to find the equation of the curve. Now, we won't do that. I've just handed you a calculator that can do all these things and do them quickly and easily. And in the next lesson, I'll show you how to get your calculator to do the regression curve quickly and easily. You won't think it's quickly and easily while we're doing it, actually. You'll think, oh, this takes forever to get the calculator to do this. When I was in practice in second year university, doing regression curves using 20 points, I think to do the 20 points, it took me 4 or 5 hours to finish the algebra that was involved. Yes, that's with checking with other people. So that's what I need to tell you. Not to show off, but just so you know, when you have to do a lot of work in your calculator and type all the points in, you're saving yourself 4 or 5 hours of work by getting the calculator to do it. In fact, when you press enter on the calculator might even think for a minute. You might get to watch the calculator have to go do, 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 do. You know, and that tells you that it's a tough math problem when the calculator has to think about it for a second. So we'll soon see how to get a graphing calculator to do regression analysis for us. There are also many excellent apps. I won't say this calculator is the best thing out there to do this. Microsoft Excel does this quite easily, and then there's many apps you can get for your phone that does regression analysis quickly. So why would you do it in your calculator if other things can do it for you? Because your calculator is available on the test and on the exam, you see? So don't practice with an outside app or something like that to do the homework. That doesn't make any sense. You might use it to check an answer. You go, I got 7.2, the homework got 7.9. You might plug it into a nice easy app and go, what's the actual answer here? And then that might make you feel better, but practice it on your calculator. More about that in the next lesson. Intervals, you've seen most of this, but I'll go over it fairly quickly. And then what I got, intervals, a little graphing, and then the number E, the best part of the day right there. All right. When working with intervals of numbers, we need to be familiar with some terminology and notation. So as you're getting used to intervals, come back to this page to remind yourself of what all these words mean. The endpoints of an interval that make up the interval's boundary are called boundary points. Oh, easy enough. You know, the endpoints are called the boundaries. You know, good word. The remaining points make up the interior and are called interior points. You might not have needed me for that. If that had just popped up the homework and they said interior, you would have gone, oh, that's probably inside the interval. Closed intervals contain their boundary points. Closed dots. You remember that from advanced functions? Closed dots means we include the endpoints, or less than or equal to. When with the equals there, we mean include the endpoints of the interval. Open intervals do not contain the boundary points. Every point of an open interval is in the interior. No kidding. So here's a little reminder from advanced functions. Here's what an open interval looks like. When the two x values at the end of the interval were open dots saying don't include a and b. Why aren't they included? Well, there's lots of reasons why they might not be included. One being maybe there's a vertical asymptote there or something at that x value. And closed intervals included the dots at the end, and we said a less than or equal to x, less than or equal to b, instead of just less than in there. So we're including those endpoints in there, and we call these open and closed. So we got to review a little bit of interval notation there, but also add the words open and closed, yeah, which I don't think I use those words in advanced functions. You can have half open intervals, that's no problem. One end's closed, one end's open, yeah, that can happen. Maybe this is a vertical asymptote, but this is an x-intercept. You know, not allowed is allowed, no problem. And this one's open and closed the other way. Any questions about those intervals? When there's multiple intervals together, I think in advanced functions, we just said and. So I said, oh, where is it increasing? And you'd go, oh, it's increasing from negative infinity to 4 and 7 to infinity. I'll encourage you to use this union symbol. And if you took data management, you might have used the union symbol a little bit. We're not getting crazy with the union symbol like they did in data management. All we're going to say is that's a nice, easy way to say, and both of these. It technically doesn't mean and, it means or. But we don't need to get too carried away about and versus or. We're just saying we want these points. We also want these points here. Yeah? Example. The graph of f at x equals x minus 3, x minus 1, x plus 2, x plus 4 is shown below. Why is this the graph of this? A little reminder about some things that you could do. You know, if you're here, you could do these things. We took care of this in like unit 3 of advanced functions. Looking at a function that's factored like this, you can easily pick off the zeros. If it's x minus 3 is a factor, then positive 3 is a 0. If x minus 1 is a factor, then positive 1 is a 0. If x plus 2 is a factor, then negative 2 is a 0. And if x plus 4 is a factor, then negative 4 is a 0. That's a crazy amount of information when it comes to graphing, actually. Having the zeros, those 4 zeros, is an unbelievable amount of information to tell you what the graph's going to look like. Yes? The only thing that's remaining is knowing that polynomial functions do one of these, both up, both down, one up, one down. You know, they do something like this, and the degree will tell you. 1, 2, 3, 4 x's with no exponents. This is degree 4 opening up, and you can use that to quickly get a little graph here. You can get the y-intercept here pretty easily. We didn't do it in advanced functions. And there's a reason I'll explain in a minute, because that's not the question I thought he was going to ask. There's another question coming. But if you made x equal to 0, then it would be negative 3 times negative 1 is 3, times 2 is 6, times 4 is 24. So you could grab that y-intercept reasonably easily. And I think we did it with rational functions. We said, oh, let's find that y-intercept to give ourselves one more point to use. There's another blaring question here, which is important for us.
How do we know whether it's facing up or down?
Oh, facing up or down. You look at these x's and you go, we don't want to multiply out these brackets. We don't want to multiply out the brackets. But if we did, what we'd find is the first term in the first two sets would be x times x squared, x times x, which is x squared. I don't know what the rest of the terms are. But then if I multiplied by this set of brackets, my next term would be now, my leading term would now be x cubed. And then my leading term after this one would be x to the power 4. So I don't need to do all the multiplication to go, the leading term is x to the power 4, which means either both up or both down, but because it's positive, they're both up. Yeah? Positive x to the 4th. Negative x to the 4th would be down, positive x, just like parabolas. Parabolas is the guide. X squared, positive's up, negative's down. The odd ones do the opposite, because they're odd. Cubed this way, or this way, depending if it's positive or negative. And you can pick off that leading coefficient without doing all the multiplication. Just multiply the 4 leading x's together, and you'll know whether you end up with positive or negative. And the degree, you'll know what exponent you'd have there. There's one more question here about this graph. We glossed over it in advanced functions. We just went, because shape was enough. What's the last question? The maximum minimums. Seems like a really big deal, especially during this coronavirus conversation. You're like, advanced functions like, oh, who cares? Goes as high as it goes. Oh, we care. It might be the most important thing in all this. What's the maximum going to be? Certainly if you're thinking going into business, you're like, how high is this stock going to go? Or how low are my profits going to go? You know, again, might be the most important thing in the discussion. We're close now. You know, within a week or two, we'll pick these off and it won't be a big problem. Yeah? Calculus will finally jump in and take care of this problem. So that's exciting. It's exciting that within a week or so we're going to knock this down. Let me not exaggerate for you. No, it might be 3 full weeks before we get there. Yeah? This week, tying up loose ends. Next week, a new weapon I need to give you. And then week 3, we'll knock this down. Okay? In quad school like this. Yeah? If it was regular semester school, it'd be more like 6 weeks, you know, before we got all that done. That's not what this question was asking, actually. It asked, state where the intervals are state the intervals where the function is greater than or equal to 0. So what I'm going to get out is my highlighter here. Pointer options, highlighter. I was playing during the last one. We want to know when is it greater than 0. So in there, and in there. And again, if this was your company, and you want to know what the profits are going to be, and I got news for you. Some companies, their profit goes like this. During Christmas time, we made lots of money. You know, from February to April, we didn't make a lot of money, and hopefully it all worked out at the end of the year. Yeah? And so the question is, when is it greater than or equal to 0? Well, 3 different sections. X less than negative 4, between negative 2 and 1, and 3 to infinity. I'm going to talk about these in a minute. I just want to talk about these symbols. See how handy that union symbol is? There were 3 different sections, and the union symbol says put them all together, all 3 of those sections.
Why are there no square brackets around the negative infinity to 4 is only the 1, and then for the 3 to infinity?
Yeah. Okay, so let's just talk about why there is square brackets to begin with. Negative 4 is included. That is because it said greater than or equal to 0. And so at 4, it was still equal to 0. So I put square bracket around to say include that endpoint. And then negative 2 to 1, those both were included. And then the 3 is included. So why isn't infinity included? Well, infinity is a dangerous deal here, you know, and is my book on the shelf here? Yes, my infinity book. Those of you who are already thinking about what you might like to do your project on for April, you could take this book and you could do your project on probably any chapter in this book called Infinity. Yeah? Infinity is a major league problem. That is, if anyone anywhere in your life says, oh, I completely understand infinity, they're either lying or they're stupid. Yeah? There's no way to completely understand what's going on with infinity. So what we have to understand is, what do we mean by infinity here? And by infinity here, we mean as big a number as you want, going that way. So that's not a great definition of infinity, by the way. But it's helpful here to go, when we talk about infinity in this course for now, what we mean is bigger than we would possibly use. That is, this graph goes to -5. Infinity to us is like -10, -20, way off the page here, as far as you want to go. You go, well, that's no problem. So still, that doesn't answer why you didn't include it there. Well, if we're talking bigger than anything I can talk about, we can't possibly include it. So infinity can never be included actually in the interval because it's just bigger than you want. It might be as simple as this. My son Bennett, 5 years old, said, Daddy, you know what's coming. Every kid asks at some point, what's the biggest number? And I said, there's no biggest number. And they don't like that answer. They're like, no, just tell me. I can take it. Tell me what the biggest number is. I'm like, there isn't one. Because if you write down what you think the biggest number is, I can always add 1. So it's like, I can always add 1 to here. So you can never include it because I can always add another one. Yeah? Did that answer that question?
Yeah.
Yeah.
We use parentheses for when it's something that you can include and then square brackets for it.
Right. Open bracket, don't include this. Square bracket, do include this. And we saw this in advanced functions, and hopefully you got less addicted to this greater than or equal to, less than or equal to sign, because this is handy. Yes? Certainly, certainly. That makes for great videos, eh? When people watch the videos online and suddenly they hear me online talking to somebody or doing something in the background. Well, I don't expect you to be like perfect at this, by the way. If you're like, oh, I don't remember all this stuff, I can, no, settle down. As you need this stuff, it will come up, and it's sort of coming up here. Like we're starting to get back to practice. You'll be surprised how much of it comes back once you get going. The first day is rough, especially if your first quad was not math-oriented at all. You know what I mean? Like, hey, math in the morning, chem in the afternoon. You'll be back rolling by Friday. You'll be like, oh yeah, we're right back into it here. You'll be exhausted, and that's when you know things are going well. And when you get so tired you can't even really see straight, you're like, perfect. Now you're a student. Exactly, yeah. Oh, the number E. Okay, completely sidetracked. Side note coming up. Like, I'm gonna get you a break, by the way, and a significant break coming up here, because our second lesson is pretty fast and pretty straightforward. But E deserves some time. We should take some time and talk about E. Separate note here, and you're going to want this. I don't know how many times you're going to want to come back to this. Maybe in chemistry class, first year university. This note is like, I don't know if I'll do a better note all year, actually, than what I'm about to show you about the number E. Well, first of all, if you want to be able to talk about Euler's number, you better know how to pronounce it. I want to show up somewhere and call this Euler's number, because the math people look at you like you're out of your mind. It's pronounced Euler. Euler was a mathematician that did some incredible work. Unbelievable, his donations to the history of math. And I'm going to show you one of his little donations here. The number E. It's got a symbol, just the number E. And the first sentence I'll write about it is a Mr. Todd original here. Well, not original. I've stole this from other people, but it's an important sentence to really establish what I'm about to accomplish here is pi is to circles as E is to exponential growth. That might not make perfect sense right now, but I'm hoping to give you a feel for the significance of Euler's number E, whatever it is. And I'm going to develop it here. I'm going to show you what E's number is and why it appears here. But first, we need a little review of the compound interest formula. And to be honest, in the middle of this coronavirus thing, maybe compound interest didn't get enough time, I just finished advanced functions, and I think compound interest was skipped over in grade 11 for those people. So I taught it to them, and gave them a couple of examples and showed them. It's not complicated, but it's important to understand. Here's the compound interest formula. I've tried to be a little vague here about what these numbers mean on purpose, because really this is just an equation of exponential growth. And I'm only going to give one example about how to use it. Because really, I'm not teaching compound interest today. That's not really what you're not going to have homework questions that say compound interest just yet. I'm just using it to tell you what Euler's number is. So, Mr. Todd invests $1,000 at 8% compounded quarterly. How much does he have after 5 years? So now I'm going to try and phrase this as if you've never seen a problem like this before, when I'm really hoping that you have, that as I'm saying these things, you're sort of going, oh yeah, I'm starting to remember this compound quarterly, it's starting to come back. But again, I'll speak like you've never seen it before. And I have to get sidetracked from my sidetrack here and talk about my son, Bennett, for a minute, who's 5 years old. And let's just imagine that Bennett's birthday is on January 1st for a second. And he comes and I say, and each year on January 1st, I give him $8 for his birthday. Now, I wish I could get out of birthdays with my children for $8. That would be great. But just for the sake of the example, because it ties together with the interest rate I've chosen here, let's just say I give him $8. And he comes to me because they've been studying seasons at school, and he says, Daddy, I don't want to have one birthday a year. I like my birthday so much, I want to have one each season. I want to have a winter birthday, a spring birthday, a summer birthday, and a fall birthday. I'm like, I like this. I like parties. I like cake. Let's do it. From now on, Bennett gets 4 birthdays a year. We'll call them his quarterly birthdays. Every quarter year, he gets a birthday. So his next birthday comes along in April, and he says, it's my birthday today, Daddy. I'm like, yeah, quarterly birthday. Here we go. And he says, where's my $8? And I go, oh, hang on. No. I'm going to buy you a cake, and we'll sing happy quarterly birthday. That's all fine. But you're not getting $8 every time. How much money is he getting on each of his birthdays if we're only going to do it quarterly? $2. Yeah, pretty obvious, right? 2, 2, 2, and 2. You're getting 2 each particular time. Better yet, how many birthdays is he going to have in 5 years? He's going to have 20 of these birthdays. So he's going to get $2 every time for 20 times. So that's why the compound interest formula looks like this for this question. $1,000 times 1 plus 0.02, and that's got to happen 20 times. Well, 2% because 8%, this actually really says that. I don't know if you ever thought about this before. That says 8%. It literally tells you how to find it as a decimal. It's got a little slash there meaning divide, and it's got 2 zeros there meaning divide by 100. That's for reals. I don't know why we don't teach it that way, because it's the perfect way to remember it. So really this was 0.08 before the question even started. And so that's why I used 0.02 there. If you really know what's going on, you don't need the 1 plus. The only reason the 1 plus in there is to help business people, remind them to go add 1 to this. Don't multiply by 0.02. This thing has to grow. So it's 102% if you want. It's growing by 1.02 every time.
So 1 plus, what is that number there on the right?
I.
I.
It's a little tiny script I. And so when you punch that in your calculator, may as well give your new calculator a test run to see if you can figure out where the exponent button is and everything like that, and make sure this all works out. 1.02 to the power of 20, I end up with $1,485.95. How many people, after seeing that full example, sort of remember the compound interest formula from grade 11? How many people are like, I have never seen this in my life? It got skipped over, to be honest, during coronavirus. It's one of those things that's like, what can we skip? Maybe we can skip compound interest, okay? That's not what I'm here to talk about today. I need the formula and I need the idea, but I actually don't care about money at all in this particular chapter. I just bring that up for now. We actually do some of this later, okay? Do you need more time for that particular frame? More time? Caught up? We're good? Okay. Back to E. To start developing what E is, I need to tell you everything I'm going to do next, I'm going to work with an initial value of $1. $1 is a great number to work with because if it happens to be $50, I can just multiply all my answers by 50. And, so we start with $1 because it's easy to work with $1. And we're going to do 1 year. Everything we do is just 1 year because, again, if it's longer years than that, then I can just change the exponent, whatever. And then finally, we're going to do 100% interest. So let's just talk about this for a second. If I start with $1, and I use the compound interest formula to get 100% interest for 1 year. This all plays out pretty nicely. It's 1 times 2, which is 2. All I'm trying to say in all that is, if I start with $1 and they give me 100% interest, at the end of the year, I'm going to have $2. Hopefully you look at that and go, I didn't need the formula for that. Yeah? So let's imagine after that happening, you go, well, I've heard of this semi-annual interest. I don't think I should have to wait till the end of the year to get my interest. I want to get interest halfway through the year, and that's called semi-annual. And if you're going to do this semi-annually, what you're going to want is A equals 1 times 1 plus, okay, instead of 100% interest, you're not getting 100% interest, because you're getting it twice during the year. This will be 0.50. You might write 0.5, but I write 50 to go, okay, I get 50% of my interest at the half year mark, but I'm going to get interest twice, so I get to multiply by 1.5 twice. And if you punch this in your calculator, you get 2.25. And we need to get sidetracked for a minute and going, wait a minute, you end up with more money if you get your interest semi-annually? How does that happen?
Because it's compounding on what you gained earlier, so instead of it being $1, 100% is 1.5.
Yeah, you got your dollar, and at the 6-month mark, they give you 50 cents. Now you got $1.50. You reinvest that and you put it in, and so you get interest on your initial dollar, but you also get interest on your 50 cents, and so you end up with $2.25. And at that point, you think you've solved the money problems of the world. You're like, well, I know just what to do here. We just got to get interest more often. Well, okay, you got to find someone to pay the interest, first of all. I mean, not everyone's going to do that. They're like, I'll be willing to give you semi-annual interest. Right? But if we could, then you go quarterly, and you go, let's just see what happens if I go quarterly and get quarterly interest. Then I go A equals 1 times 1 point, oops. Writing too fast for my brain now, or I can't write fast enough, or I don't know what's happening. 25% interest, because there's 4 times that I get interest, but that happens 4 times. And you think you've broke the money system at this point. You're like, oh, this is going to be good. This is going to be way better. 1.25 to the power of 4. Now I end up with $2.44. Well, a lot has happened in a short period of time. At first glance, you're like, see, I was right. I'm getting more money. I'm like, yeah, you are, but what happened? 2 to 2.25 was a big jump. 2.25 to 2.44 was not as big a jump. And the question is there a limit, he said, starting to teach chapter 2 already, is there a limit to this process? Does this keep getting bigger and bigger, or is there some stopping point here? Is there some point where it's like, no, and that's it? So I'm going to jump ahead. Instead of doing quarterly, I'm going to jump all the way to monthly. You know, the next one might be every 8th year, but nobody does everything 8th year in business. Quarterly is the most common thing in business because it takes them 3 months to do their paperwork. So we do it every 3 months. Monthly is the next one because when you buy cars and houses and so on, you want to pay monthly because that makes sense. So if I go to monthly, then I get A equals 1 times 1 plus, let's see, 1.00 divided by 12, but I get that 12 times. I'd practice right now. I'd see if, without figuring that out beforehand, see if you can type that whole line in your calculator. 1 times 1 plus 1 divided by 12, close the bracket, exponent 12, and I get 2.613. I jump to monthly and I'm still losing ground. You're like, no, you're gaining ground. That's not what I mean. I'm gaining money here, but I'm at a lower amount. This went up by 25 cents, then by 19 cents, then by 17 cents.
Well, I mean, for the first one to the second one, it was half, and then it's a quarter, so it's a half of a half.
Yeah.
But you're only gaining half the value that you were gaining from the previous one when you're affecting.
Yeah, the payoff isn't as good as we thought it was going to be. That is, I split off my money to $1.50, and each of those guys got interest, and it was good. But as you're doing these splits, the splits are getting smaller, and the splitting is defeating the compound interest at some level here. We're losing ground. We're gaining ground, but at a losing amount. Yeah? What I mean by that is, I'm going to jump to seconds here. I want interest I don't want to wait half a year for my interest. I don't want to wait a quarter year. I don't want to have monthly. I want interest every single second of the year. And I'm going to use a word that's not really a word. Secondly. Every second I'm going to get interest now. A equals 1 times 1 plus 100 divided by, how many seconds in a year? Okay, this isn't as bad as it looks. 365 days times 24 hours in a day times 60 minutes each hour times 60 seconds. There. I'm not going to actually figure it out. I'll let the calculator take care of this for me. And then up here, how many times do I get interest? 365 times 24 times 60 times 60. Try typing that in your calculator and see if you can land it. I'm going to use my fraction button on this calculator to do this. Oh, the fraction button's not working on my new calculator. I'll show you in the second lesson. We'll get all that stuff figured out. So again, if you can't get it to work out, don't panic. You know, let's just practice with the calculator a little bit. I might not get the second lesson done today. That'll suck on all my plans. But anyways, fraction button, 1 over 365 times 24 times 60. Oops, I almost forgot a 0 there. Times 60, close bracket, exponent, 365 times 24 times 60. I get 2.718. 281615. Pretty unimpressive, actually, from a certain point of view. Because I just jumped from monthly to secondly, and I went from 2.61 to 2.71. Last one. 100 million times. Not just every second. I essentially want interest every moment of every day. All the time I want my money making interest here. And so I'm going to go, do I know how to type 100 million? I don't know. 1 plus 1 over 100 million. And up here, 100 million. 8 zeros. One plus 1 divided by 1. I'm going to go 8 zeros. 3, 4, 5, 6, 7, 8. Close bracket. Exponent 1, 1, 2, 3, 4, 5, 6, 7, 8. 2.7 1828, 1815. Really unimpressive what just happened there. This is Euler's number. Euler realized that there was some natural number to growth. And if you look in your calculator and look for an e button and you go e to the power 1, well, I might be off a decimal place here at the trillionth level or whatever it is, tenths, hundredths, thousandths, 10,000, 100,000. I might be 1/1,000,000th out, but that's what Euler's number is. It's somehow essential, natural to exponential growth here. And it has to do with biological processes don't increase, they don't suddenly double. You don't suddenly go from 2 rabbits, or sorry, from 1,000 rabbits, and then on January 1st you look and go, oh, now there's 2,000 rabbits. You know, the rabbit population just goes continuously like that. And if things are doubling consistently, really the growth rate is this, 2.718, because some of the rabbits have already made new rabbits by now. Rabbits are great at this. It doesn't take long for little rabbits to make more little rabbits. Yeah? So biological processes and things like coronavirus, this is a more natural growth rate of doubling. I don't expect you to understand that perfectly, but it is a good note to go back to when you're like, what are we even talking about with Euler's number? Let me finish the last slide and get you a break. The number E is known as Euler's number, named after the famous Swiss mathematician Leonhard Euler. The value of E is approximately 2.71828. Like pi, it's very rare you need more than 3.14159. You know, this is enough decimals for a lot of stuff you do, but we don't have to worry about that. We got a calculator button that does E now, so we don't have to worry about that. Similar to pi, E is a rational number. It cannot be expressed as a fraction. It can't be expressed as a quotient of integers. We don't need this, but it's important to know that E is also called transcendental. It's not the solution of some kind of polynomial equation. You never go p at 1, p at -1, p at 2, p at -2, p at E, and it works, and it never works out. And it's very difficult to prove the number is transcendental. And as you will see, E is a very special number when working with exponential functions and rates of change. I only mention it for today. In tomorrow's lesson, I'll bring it up a little more. Yeah? And the value 1 plus 1 over n to the n, which is essentially what I just did, approaches E as n approaches infinity. I used 100 million. I didn't go any farther than 100 million. But essentially, that is E. That's how you get E. A very large n, using this, you'll get E. The idea is related to the concept of continuously compounded interest. Any questions there? For this lesson, it's just like, here's E. That's all we're asking in this lesson is let me show you E. We don't go any farther with it than that.